Okay, time to talk about hydrogen bonding. So this is our last form of intermolecular bonding, and it's a further type of polar bonding, but it's got to do with, you guessed it, hydrogen. So this is my little rule. It's like HFON. Yeah. So when hydrogen is bonded to fluorine, oxygen, or neon, nitrogen, then we have hydrogen bonding. So any polar molecule that has these bonds, yeah, one between oxygen and hydrogen, fluorine and hydrogen, or nitrogen and hydrogen, you're going to get hydrogen bonding. So this is the last little synopsis on your notes. So it says there is one more type of intermolecular bonding. This bonding always involves hydrogen, which has a moderately low electronegativity, combined with a highly electronegative element such as fluorine, oxygen, or nitrogen. And I'm just going to show you why, but I need to get my electronegativity table. So let's use this table to figure out why, in particular, hydrogen and these three elements. So you can see hydrogen over there at 2.2. Then we've got nitrogen, oxygen, and fluorine are all above 3. So let's just try and put them into our notes here. So we've got hydrogen is 2.2, 3.04, 3.44, and I'm pretty sure the last one was 3.98. That's correct. 3.98 electronegativity for each one of these. Now you can see because there's quite a large difference between hydrogen and these, this is what's going to help us. So this type of bonding, so we're now in the second paragraph, this type of bonding explains why water expands when it freezes. It also explains why water, ammonia, and hydrogen fluoride have much higher melting points than we would predict from those of a similar sized polar molecule. So if you remember back when we related size to boiling point and melting point, this is the reason why water didn't fit that pattern. So it's anytime hydrogen is bonded with fluorine, hydrogen is bonded with nitrogen, or hydrogen is bonded with oxygen. So let's just have a look here. You can see that here we've got hydrogen fluoride on the left. We've got water in the middle, and we've got ammonia on the right. So in compounds, this is now the third paragraph, in compounds containing hydrogen, or H, and one of, F, O, and N, the bond between the hydrogen atom and the highly electronegative atom is so polar that the hydrogen atom builds up a substantial amount of positive charge. Okay, so all of these hydrogen atoms have built up substantial positive charge. So the hydrogen atom is therefore attracted to the non-bonding electron pair of the FON on another molecule nearby. Okay, so all of these you can see here are the lone pairs for the nitrogen, the oxygen, and the fluorine, and that's what we're attracted to. This is directional. Okay, so it says the hydrogen atom is attracted to the non-bonding electron pair on the FO or N atom of the adjacent molecule, which has that buildup of negative charge on it. This highly directional force of attraction is called hydrogen bonding. So anytime there's an O on one side and an H in the next molecule, you're going to get lots of nice hydrogen bonding there. So hydrogen bonding is the strongest form of intermolecular bonding, but it's really important to remember that it is still much weaker than any other type of covalent and ionic bonding. In particular, in biology, we learn about hydrogen bonding being really weak. And so therefore it's easily overcome by temperature, whereas the covalent bonds in the backbone of DNA, for example, are really hard to break. So there's my little link, can't help myself. So why exactly does ice float? So on the left here, we've got a picture of what liquid water is. You can see that the molecules are moving past each other a lot. So the molecules moving past each other, but as they start to slow down, what happens is that kind of attraction, that really strong force of hydrogen bonding, forces them into a lattice. Okay, so they forces into what we call a crystal lattice, which is why ice has crystals. So it forces them into a crystal lattice. That means there's more space in between each atom. That means they are less dense, yeah, less molecules per mass, and therefore they will float on top of liquid water. So just finishing off the page on hydrogen bonding. Hydrogen bonding accounts for why ice floats on water. As the water molecules arrange themselves into a solid, each molecule forms hydrogen bonds with 4 other molecules at particular angles. You can see these particular angles in this picture here. And they become shaped into a regular crystal lattice shape that pushes the other molecules further apart than in their liquid state. This means that ice is less dense than liquid water. Once melted, the water molecules are free to move around each other. If the temperature is increased, then what's going to happen, so if you increase the temperature of this one on the left, so you increase its temperature, then eventually you're going to overcome these regular lattice bonds and you're going to end up moving them, they're closer together. So it says, if the temperature is increased, the movement of the molecules increases and eventually they start to move apart again. Therefore, on heating, your density actually decreases. So you can see over here, we've got sorry, it's the other way around. On heating, the density starts to increase. Oh, sorry, this is talking about, your paragraph here is talking about what's going to happen when you go to a gas. Okay, so you're going to increase your energy. And as you increase your energy, you're going to end up breaking apart these bonds even further and you're going to become less dense again. So the most dense form of water is not its solid form, it's actually in its liquid form. So we've now finished all the different types of intermolecular bonding. Here are some of the questions that you've got to move on with and where you can go in question time.